Standard entropy values have been assigned to different chemicals, and these values are assigned based on the third law of thermodynamics. The third law of thermodynamics says if you could get to absolute zero, the entropy of a perfect crystal would be given a value of zero. Now, from there, you can do calculations to calculate the entropy value at room temperature. We're not going to go through those calculations in this class. What's important is you're able to look at a standard entropy value and understand why one value is larger than another. So, for example, water in the liquid state has a standard entropy of 70 joules per Kelvin per mole. In the gas state, it's much higher, 189, because the entropy of a gas is larger than the entropy of a liquid due to the randomness. Gas particles can move around in a random motion much more than liquid particles can. You see another trend as the molar mass goes up, the standard entropy goes up. Argon and xenon are both gases. Xenon has a larger molar mass. The standard entropy of the same state, but larger molar mass, is usually higher. Some elements exist as allotropes. So, for example, carbon can be found in the diamond or in the graphite. Diamond is a three-dimensional array and graphite is two-dimensional. The particles in diamond have a lower entropy value because they're more ordered. Graphite is more random because it's only a two-dimensional bonding. And if you have the same number of carbon atoms and hydrogen atoms, you're going to have the same molar mass, but you can have different bonding connections. So if you have something like this, where you have 6 carbons in a straight chain versus 6 carbons, but there's more branching here, the larger value of the entropy is from the one that can undergo more types of motion. Having branching means there's more types of vibrations that this more complex molecule can undergo compared to a straight chain. We're also going to look at changes in entropy for a chemical reaction or a physical change. So, for example, if you had this reaction between sugar dissolved and sugar solid, the more random side is dissolved sugar. And when the reactant side rather, is more random, the change in entropy is a negative number. When aqueous sugar turns into solid, that creates order, it decreases randomness, and the entropy change is negative. If you reverse this reaction, if solid was turning into aqueous, then the entropy change would be positive. Here's a chemical reaction between 3A and 1B makes 4C. Notice we're changing the number of moles of gas. Gases have the largest degree of randomness. They have the most entropy. So in a chemical reaction that involves gases, if the number of moles of gas increases, like it does in this example, then the randomness increases. Delta S will be a positive number. Here's a phase change between a solid turning into a liquid. The liquid side is more random. Delta S should be a positive number. You can also use what you learned before to figure out the heat change or the enthalpy change. For a solid to turn into a liquid, the solid has to absorb heat. And when heat is a reactant, delta H is a positive number. For a phase change like this one, you can calculate the change in entropy instead of just knowing it's going to be a positive or a negative number, because at constant temperature, the change in entropy is equal to Q, the heat, at constant temperature, that's the subscript T, divided by the temperature in Kelvin, Or another equation we're going to use a lot, any reaction or phase change at constant temperature and pressure, delta S is equal to delta H divided by T. So here is that cesium example, cesium solid turning into cesium liquid. The temperature where this is at equilibrium, that's the melting point, also called the temperature of fusion, is 302 Kelvin. Delta H, we predicted it should be a positive number because it's an endothermic reaction, and we can calculate delta S by using this formula, delta H divided by T. Delta H divided by the temperature is going to give us a positive 6.95, and notice the units are joules per Kelvin per mole. So we predicted this should be a positive delta S because solids melting creates more randomness, less order.